In geometry, a square number represents the physical area of a four-sided shape with equal sides. Finding a square means multiplying a base number by itself, signified by a superscript 2. In a grid, multiplying a base of 3 by a height of 3 creates an area of 9 units that lock together into a perfect square. This is the core of the concept. Any perfect square is simply a number that can be arranged into an equal-sided geometric grid. The mechanics of multiplication create rigid patterns in how square numbers end. While the final digit can't always confirm a number is a square, it allows us to immediately identify numbers that are impossible. As seen in property 3, every perfect square is restricted to ending in 0, 1, 4, 5, 6, or 9. This creates a rapid elimination tool, shown in property 4. Any number ending in 2, 3, 7, or 8 is impossible. For example, 122 and 153 are rejected instantly. Finally, property 2 states a square can only end in pairs of zeros. An odd number of zeros means it can never form a perfect square. These ending digit patterns function as an immediate filter. They help you strike out incorrect answers before you ever start a heavy calculation. Finding a square root is the inverse operation, the process of working backward to find the original base number. We use the radical symbol to indicate this. Since 5 squared is 25, the square root of 25 is exactly 5. With prime factorization, break the number into prime components. Then, group identical numbers into pairs. In example 4, 196 yields a pair of 2s and 7s. Extract 1 from each pair. Multiplying that 2 and 7 together reveals the square root, 14. This pairing method is reliable, but as numbers grow into the thousands, listing every factor becomes inefficient. For massive numbers, we need a more powerful algorithm. This is where long division excels. First, group the digits into pairs starting from the right. In 529, the 29 forms one group, leaving the 5 on its own. Start with the leftmost digit, the 5. Find the largest perfect square that fits inside it. 2 squared is 4, so place the 4 under the 5 and write 2 in the quotient spot. Subtract 4 from 5 to get 1. Then bring down the entire next pair, the 29, to form our new working target, 129. Next, double the current quotient. The 2 becomes a 4, placed to the left with a blank space waiting for a new digit. We need a digit for that blank. The new 2-digit number, multiplied by that same digit, must reach our target. 42 times 2 is 84, but 43 times 3 hits 129 exactly. The square root of 529 is 23. Pause the video here and try this sequence yourself. Use the long division method to find the square root of 784. Let's check your work. Following those same steps of grouping, doubling, and finding the multiplier, you should arrive at a final quotient of 28. This algorithm may feel complex at first, but mastering it ensures you can solve any large perfect square you encounter. We can now assemble a complete toolkit. Remember, square numbers represent a geometric area, and their roots are the length of a single side. Use the elimination rule for your first check. If a number ends in 2, 3, 7, or 8, it cannot be a square. Then select the best method for the size of your number, prime factorization for smaller values, and long division for everything else. Apply this logic to a final challenge. Could a square playground with an area of 1,000 square meters have sides that are whole numbers? Since 1,000 ends in 3 zeros, an odd number, it fails the requirement. The sides cannot be whole numbers. These patterns provide practical, immediate tools for understanding the dimensions of the world.